Hello, my name is Judy. I'm a PhD student in University of Namur, Belgium, under the supervision of Dr. Alicia Ferrante, Dr. Elio Tucci, and Dr. Giulia De Masi. In this paper, we studied the interplay between differential option quality and differential quantity of individuals with fixed option, which we call them zealots, in the best of n problem with n equals 2. The best of n problem is a discrete non-continuous consensus achievement in collective decision making. The swarm has to collectively choose one of n given option, and that has to be the one with the best quality. The typical scenario for this is when a swarm of bees has to choose their new sites. In this example, we have two site options of their new nest A and B, where B seems to be the better one. The swarm will send out scout bees. In this example, the scout will explore site A and site B respectively, and they will come back to the nest and start advertising their findings. Real bees will do wiggle dance. Our robots represent this with dissemination mode. The better the quality of the option they just visited, the longer they dance. In this case, the agent who visited site A has stopped dancing and observed that her neighbor who visited B is still dancing, indicating that site B has a better quality. This mechanism is called positive feedback modulation. There are two possibilities in this photo model situation for the agents who has stopped dancing earlier, whether it will keep its opinion to A or change opinion to B. In this example, it changes the opinion to B. So subsequently, they both will explore option B and later will come back to the nest and advertise for option B. The process continues until all agents chooses option B. As the focus of this research is to study differential quality versus differential zealotry, we use two kinds of agents, normal and zealots. Normal agents are able to change their opinion by randomly adopt the opinion of a random agent in local proximity, as we saw in the previous slide. Zealots, instead, never change their opinion and keep the one they have at the very beginning, either A or B. Hence, it can influence other normal agents, but never get influence. So we want to know, can the option with lower quality, in this case A, to win against the better option, which is B, with the help of zealots? Our experiment started by having the same quality and the same number of zealots on both option A and B. With this setup, we run the simulations for 40,000 time units, repeat it for 100 times, and take the mean consensus value. Then we increase the quality on option B and keep the quality on option A. We make A as the option with the lower quality. Then we start adding the number of zealots on option A while keeping the number of zealots on option B. And then we observe the result. And we keep on doing that. Programmatically, the simulations arena looks like this. The original code was written by Gabriele Valentini, and we added the zealot agent feature to it. Side A and Side B are the options explored by each agent. The nest is where the dissemination and voting happen. Each agent has the same limited sensor range, so they can only see nearby agents when doing the voting. The results are very interesting, and we put them on heat maps. The color scale indicates the level of consensus achieved. Dark blue colored region shows the perfect consensus to B, which is the option with the best quality, while the red cells indicates perfect consensus to A, which is the option with lower quality. Paler colors here indicate weaker consensus states closer to 0.5, and the white curve is the indifference curve separating consensus A from consensus to B. From this figure, we can see that as the quality difference is going up, the swarm tends to choose the right option, even when the zealots for the low quality options are 5 times more numerous. We found that the quality of an option is more influential than the quantity. Yes, it is possible to influence the swarm to choose the bad option, but it takes very high number of zealots. We also run simulations with different swarm sizes and different proportions of bee zealots, but they show similar results. This study can be extended in the future by studying the effect of higher number of options and by adding a mathematical model to have a better understanding of the dynamic of the antagonistic settings. On behalf of the authors, we thank you for attending this presentation. Have a good day.